Okay, it looks like we're up and running. Up, got the hat off. Time to come in off of the cold out there. I come in out of the cold. And this video is going to be about finding volumes of different types of situations. Um, Boxes, volume of pottery coming out of the ceramic studio, things like that. Okay, let me get a full screen. And let me pin the video here. I don't have to pin it. I'm the only one on. Although every time I log in with this Zoom, it seems like people's phones automatically. I don't know. I don't understand this technological world. All right. So what do we want to talk about here? Let me think. We're going to learn how to find the volume of this fresh and simple sour cream, no preservatives hood product. There it is. I put it on the x-axis. That's the scissors. And we're going to learn how to find the volume of this Kleenex box. When I superimpose it on an XY axis. All right. So really what you're practicing here is you get to decide what to write in the integral. To this point in time, I've been giving you things. I've been giving you integrate 2x squared minus 3x plus dx from a to b, different numbers, and that's an actual number. And we've been looking at, so let me put a 5 here, 5 to 7, that's an actual number. Oh, okay, when we put an x there, well, that's an accumulation function. Depending upon where you are on the x-axis, you're measuring amounts under this curve. And of course, if I put x squared there, then this is no longer the derivative. It gets a little more complicated, and that actually is where the chain rule is coming from. And we're going to examine all of those things in the second half. But honestly, they're all based on integration. All of those topics are based on integration, so we're having the same conversation daily, or we're going to have the same conversation. It's just from different perspectives. Now, what comes out of this particular topic, not that you can find the volume of any of those things. That's not really the issue here. The issue is you now get the marker and you look at a situation and you define the rate of change. Okay? And that's really what we're practicing, is putting the marker in your hand and saying, I got a situation here. What do I need to write to actually figure this out? That's the beauty of this moment of study. So I want to take you out of the mechanics of, this is how you do that particular situation, to your first attempt at looking at something and figuring out something from scratch. All right, that's the beauty of this. And to get started, you want to think of a loaf of bread. A loaf of bread that comes from the grocery store, that's in one of those nice little twisty things and they're wrapped up, and it actually comes to you in slices. Okay, and that's what integration is. Integration is all about slices and defining one slice. And then as you add up those different slices, which can be in differing amounts. I mean, you've done the Riemann sums, you've done the left-hand rectangles, right-hand rectangles, and sometimes, one slice is different. This slice of bread is going to be different than that slice of bread, right? I mean, this has got a bigger Y value to it. Right? So as you add up something from left to right, each slice is different based on which X I give you. Okay, so we'll get into it in a moment. And I haven't prepared any statements. This is just off the cuff. But I could print out your, oh geez, drop something here. Yeah, I could print out your test piece of paper, right? This is a layer. I put it on top. I put another one on top. I put another one on top. And before you know it, I'm building a volume based on the area of one slice and a little bit of thickness, right? And in this case, actually this would be in terms of dy, because the thickness that you're looking at right now is a vertical thickness. But if I added things up, slice in that direction, we'd have to do it in terms of change in x, because if you can see this, but then this has an x1 on this side and x2 on that side, and that little bit of difference is your dx. So we're going to be doing these calculations. Some of them will be done in terms of x, which means that we're saying y as a calculation based on x values, right? So our altitudes are based on calculations we're performing on x. Again, back to Riemann sums. Now, if I told you that I wanted you to add something up from left to right based on the ln function, right? I mean, I'll give it some justice here. Based on the ln function, then depending upon what x you're working with, that defines that y value. Okay, but we could be looking at some x value based on y. So we could have integration where we work with what are we doing to y's to get x alone. Okay, so that's going to come into play. All right, so there's the spiel. Let's actually do a problem here. Let's actually go back to, where's my scissors? All right, let's actually compute. All right, so what do we have here? We have something that's my x-axis. I'm going to play with this just a little bit. That's my x-axis. We'll blow it up. There we go. And we're going to rotate. We're going to take this y value, which we're going to have to define in terms of x, and we're going to rotate it around the x-axis. Okay, excuse my drawing again. Third grade was about it for me. So what we really have is, if I slice it, here we go, slice it. There's the top of my coffee cup, right? There's the little drops of coffee, just finished it. It was very good. Thank you, Dining Hall. Okay, that's a slice. And so what do you see? It's got a little bit of volume to it. Well, I hope you see that. Oh, it's circular in nature. And I think we're looking left to right. So we're going to do this in terms of dx, although we could have, done another one in terms of dy. And we'll get to that. We'll practice that. This is just the first foray, our first jump into the topic. So that'll be our word of the day, foray. All right. And we have to define this. Well, I think the area is defined by pi r squared. I think it's circular. With a little bit of thickness, gives us one slice from left to right, right? If I kept this slice actually is in the interior of the, it's inside there, right? And so those coffee cup tops get smaller here. They're smaller coffee, and then they get bigger as I move to the right. All right, so let me erase this now, and let's get a function that we can work with. And we're going to do a disk method, it's called. So this is the disk method of getting us started. So let's get a function we're somewhat familiar with. How about I take the square root of x and move it up 4 units? And it grows slowly in the right direction, increases slowly. Concave down. Oh, yeah, we could get into first derivative, second derivative, prove that it's always concave down. So this is our function, square root of x plus 4. And so that circular one, that coffee top of the lid, here we go. Saturday morning, it's early here. The lid in the interior is bigger, right? If I, where's my lanyard? Oh God, I have it here somewhere. It's there. All right, hang on. Nobody in the building. I'm taking the mask off. All right, if you're worried about me, put your masks on. There we go. Let's get started here. Let's find this. Can I find it? Yeah, come on, you're there somewhere. All right, we're working on it. Hey, this is fun. Let me get it. There we go. Don't lose the sweats. Here we go. You're there somewhere. Come on, baby. Where are you? I can't find it. Look at that. There it is. Oh, there it is. Okay, I got it. This is a good video. There we go. I got the lanyard. All right, so what we're basically, I'll do my picture here. Now the FBI knows where I am. I swear I wasn't at the Capitol. I swear to God I wasn't there. All right, I'm going to rotate it around, goes behind the board and comes back. And I get what's called a volume of revolution because there's a little thickness to this part of the lanyard, right? it's thin, but as I rotate it around, oops, very bad drawing, should have been lower. I get one slice, and that's all I got to do is I have to define this slice. So let's take a gander at it. So there's the thickness. So what does that become? Well, I know that particular y value comes from taking this x, plugging it into the square root, and adding 4. But geometrically, what did it become in this example? Well, I hope you see it as the radius, right? And those radii are going to increase in height as I move to the right. But one slice is area times the width of that radius, which is our dx. And we're going to add that up from, let's go from 0 to, how about we go out to 5 here? 0 to 5. So we know 0, yeah, you can see that. 5, well, again, we got a geometric representation for area of a circle. It's pi r squared. So all this is that's my r. So I got to do pi parentheses square root of x plus 4 squared. That's the area. And if I give it a little bit of thickness, that's going to give me the volume. If the sour cream, is this sour cream? Yeah. If the sour cream was in this little container, then we just measured how much sour cream is in it. Oh, I know it's net weight, 16 ounces. It's, well, whatever. Okay. So that's how you could find the volume of that critter. And, you know, I'm going to do one for you first day back Monday. But this gives you a little peek at what we're doing. So we're going to have, for instance, finding how much water maybe something coming out of the ceramic studio can hold, or things of that nature. So let's say that somebody's on the potter's wheel and they do one of these little critters, right? Well, here's, okay, this is how bad I am. Boom. Yeah, that's pretty good. Right there, right? There's a pot somebody made over in the ceramic studio. And we want to measure, let's say that we fill it in with something. We want to measure the volume of whatever we put in there to fill it in. So let's talk about, oh, this is a function. Oh, there we go. Looks like that y value, how about I, instead of saying y, I actually say the radius is based on the x that I put into the calculation. Looks kind of like a trig function. All right, so yeah, I could come up with a pretty quick trig function here. Well, I'll do that later on my dime. So right now, we've got from A to B. All right, so we're going to integrate from A to B, an actual amount here of, well, is it okay if I take the pi out? It is a constant. So let's put it out here. It might be easier to do that. In fact, that's what we're going to be doing. And pi r squared is, well, this measures the radii dx. And that calculation will get us the volume of this ceramic piece. And then the next thing we're going to do is, and I'll take, let's see, where's my next one here. So I got another one actually. I hope I don't put this through my hand. Got to put it through the x-axis. Oh God. Oh God, I'm going to hurt myself. I know it. I don't want to slice my, anyways, you get the picture. Here you go. So here's another disc, right? And what if I wanted to talk about, leaving that as open space, but just how much material did it take? How much material did it take to make this piece? Well, then we would be subtracting. Let's move this over this way. A different disc. Let's call it g of x. And g of x is a little small. So let's do the same picture here. Fx, g of x is this one. Right? So I would have to have this one minus from A to B of pi, excuse me, the pi is there, right? Pi. Let me get that bigger so it's on video a little better. Minus pi from A to B. G of x is the radius of the interior disk from A to B, and of course we're going to pi r square it, dx, and that would find this material here, how much there is. And it usually takes a while to get the ability to write these quickly and easily. Classes take a while. We have some functions. It's hard, it's easy to mix things up. But we take this now and we write it as a singleton. And as a singleton, it's pi integration from A to B f of x squared minus, I'm going to put the 2 here, right? F of x squared minus, let's keep it in parentheses. F of x squared minus g of x squared, boom, boom, dx. And that's called the washer. It's kind of like Dunkin' Donuts, you know, and you're measuring how much donut you're getting. And you're not eating anything. Empty space, right? Final frontier. No, space is the final frontier. Empty space, therefore, is the beginning frontier. Okay. So those are the disk method and the washer method. And then we're going to do it in terms of X and Y, so on and so forth. But we don't have to do just volumes of revolution. We can figure out the volume of the Kleenex box. All right, volume of the Kleenex box. Where's my Kleenex box? Here it is. By talking about cross sections cut perpendicular to the x-axis. Oh my God, what an awful thing to say. Perpendicular cross sections cut perpendicular to the x-axis, and adding up the shape we see. I don't want to get this too complicated. It's really okay. So that's what you're looking at. Okay, and it looks to me like if we sliced, I could peel this part of it. And there's a slice. Let's get this slice. Oh God, I'm gonna lose my Kleenex box, and I need it. There we go. Anyway, if I ripped off the tab and the tab and the tab, we'd have just one slice of bread there. One slice of bread. Oh God, I'm gonna stop right there. And it looks to me like which way do I want to do this? I guess I got to do it this way. Or if I'm going to go left to right, or I could do it this way. I go left to right. Okay. The height would be determined by a constant function, right? But let's pretend it's got a little wave to it, right? And I want to measure the volume of whatever that kind of box looks like, a wavy box, right? And I can see that my heights are a function of x again. And it looks like those heights, looks like the width of the box is about twice that. That distance there is about twice that. So let's say that that is your height, or your function, that's your height. And the width of the box is twice that, 2 times f of x. And what you'd get is, you'd get actually this area right there, that area. Right? And we need a little bit of thickness, which would be if I cut it right down from here, cut it right, there's your slice of bread, there's your thickness. And if we added that up from left to right, whatever, that would be measuring the volume of the box. Now, I'm sure everybody, well, I'm not sure everybody, but most everyone hopefully knows how to swim. And I had a lake place once, and used to go out swimming all the time in the summer. I used to love to go down the bottom of the lake as far as I could go and just peace and quiet, see the old fish, but deeper I went, more pressure I felt. And if you think about integration, I always think about dams, how much pressure can a dam hold? I think it's important to know, especially if you're living, just downriver from the dam. And this is what integration finds. Integration would allow us to add up each, as water comes in behind that dam, gets higher and higher. Think of a layer of water, just a little bit of layer, adding up all those layers, pressure on the dam. There's applications to this stuff going forward. So again, it's a first foray into this. Repetition is our friend as we begin our practice. Doesn't matter year to year to year. It always feels awkward getting started on a topic like this, but we refine our conversations. And once we're in class, we can have individual conversations about what's going on. It's far better instruction than just trying to do a problem with me. All right. And we got the whole second half once we get these topics in front of us. I'll give you one. I think I ought to give you an example of one here, and you try it now. All right. So let's see. So we're going to rotate, and we'll actually do it out. Find the volume of, I've got to remember exactly how I want to phrase these questions. Find the volume of revolution created when y equals f of x, which equals, how about we do y equals x from, how about we go from 0 to 10. From x equals 0 to x equals 10, find the volume revolution generated when the function y equals x is rotated around the x-axis from 0 to 10. There, I'm trying to remember how I said that last year. I think I finally said it correctly. Okay, so pause the video, you try it. Okay, you're unpaused now. I don't expect you to have immediate success here. It takes about 4 days just to get a sense of what the heck's going on with a lot of topics that are introduced that are new. But the first thing you should do is graph it. Here's y equals x. We'll go from 0 to 10. And it looks like when I rotate this, I didn't put my lanyard away. Oh, good. Looks like when I rotate this around the x-axis, and this is y equals x, right? I think I'm getting a cone. I should have brought in one of the orange cones from the practice field here. I'm getting an orange cone that we put out, and we're not going to have empty space inside. It's cheaper if you have empty space. You don't have to use as much material. But we're going to assume that it's a solid revolution. Okay. Well, that means that as I go around the x-axis, right, one slice. There's one slice. Turn it this way. Right. What I've shown you is something that I've kind of done to the side here, but we're going to rotate it so it's facing you like this. Again, can I go through this? Did I ever break this one up? Oh God, I'm going to put that through my finger. But it's one slice. All right. So what do we actually have? We have a cone. I actually think we have a geometric formula for a cone. I think it's 1/3 pi r squared. Maybe we'll generate it right now. So that x, that y value is actually whatever x value you're at on the x-axis. Obviously, if this one 0 to 10, that might be at 4. The next one might be at 4.01, just a little bigger. 4.02, just a little bigger. And we're going to add up all of those chunks of volume from left to right. And if we do, we're going to fill this thing in. All right, so what do you have? From 0 to 10, pi r squared in this case is x is determining each radius is x units high. You're squaring it. Dx, we can do that one pretty easily. Pi x cubed over 3. Oh, there's your pi r cubed over 3. There's your volume of a cone from 0 to 10, and you've got it nailed. That's it. We could have done it from 0 to 10 in terms of y. If there, we could have done it vertically. We could have gotten the same cone done vertically. It would have been this way. All right, and then we've got these x distances are computed by the y value. It's actually the same. It's still 0 to 10, but it's vertical. 0 to 10, but now I have pi y squared dy. Nothing new, just different perspectives. And anytime you do a different perspective, brain's going to slow down for a while and sort it out. And hopefully, 2 weeks from now, what might be looking complicated, like so many of the problems that you looked at before, right? I mean, the first meeting was 25, I think. The second was in the 30s. And then the third one after break, same place, because we weren't practicing. We got away from it. It was a little higher, but scores fluctuated. The next test, test 4, definitely was higher. I think it was, significantly higher. The last one, I haven't finished grading, but right now, got a 79 I saw, a couple of 76s, and I've only graded 7 papers. So that's out of 81 points. So what was hard for you? Day 1, midterm, a lot of things. And I saw some real progress from some people. I just skimmed some tests, saw some real progress from some people who hadn't too many things in their pocket, threw some things in their pocket on that last test. That's encouraging because whatever still isn't in your pocket, it ain't going away. We're going to keep looking at it, and we got a month anyway. Maybe, I don't know, what do we got? Another 6-8 weeks? March 8th, I think. So we got some time to put those in your pocket, as well as the 5 new topics that we're talking about. That's what I'm going to grade you on. And for those who put it in their pocket, what I'm grading you on, then I'm going to throw you some nice challenging problems from another level up. Still integration, differentiation, everything we're doing, one or the other. And that's where we're going to go. Okay? So it's a little awkward, this conversation. I feel like I'm not saying it as well as I want to, but as an instructor, repetition's my friend. A week from now, I hope I'm saying it more smoothly, more succinctly. Oh yeah, succinct, one of our words, yes. Yeah. Saying less and doing it better. And I hope that eventually that this type of problem at the end of the term is perfunctory. You just know how to do it. Don't have to study for a final exam. Got it in your pocket. Just like chain rule now is in your pocket on many of the functions that you've memorized. And just perfunctory, I just do it. Implicit differentiation, I just do it. Obviously, I can raise the level and will to different calculations, but if you get it in one place, you put the effort in, should be able to do fine. Okay, very pleased with what I'm seeing coming my way from midterm, and we'll go from there. And if you're struggling, and some folks are still trying to make connections. Math help Monday night, Wednesday night, Zoom, a one-on-one with you, and we got some gaps to fill. Some of you are still writing your trig functions as, it's the cosine of x times x minus pi over 3 plus the sine of pi over 3. Well, we got to clear that up. That means you just didn't learn what you needed to learn at the last level. And that takes some extra work because that's a prerequisite of the class, that you know all these things. And obviously, some folks, whether it be pandemic, didn't get enough trig practice. I don't know, but you can start with my YouTube channel. There's 2 videos on how do you evaluate the cosine of pi over 3. It's from scratch. So please go there. All right. And then we'll do some one-on-one work if you don't get it. All right. I'm rambling. That means I got to shut the video off.